this computer. Okay, there you go. Now we're recording. So circuit reduction means that if you have resistors in series, which would basically mean that you have them something like this, right? So they have, starter nodes, ending nodes, like that. Like if this is like 2, 2, 2, you can combine like 2 ohms. You can combine all of these into one big resistor, which would be a 6 ohm resistor, right? The reason being because resistors in series reduce voltage, but they don't reduce current. So if I have like, let's see, what's an example that I can kind of like, well, we can actually use this. Let's just go off of this example, the one that we have above here, right? So here we have shared nodes between these two here, right? So 9 and 7, meaning that we can redraw this circuit. Oh, another iPhone is coming in. All right, come on in, iPhone. All right, so the 9 plus 7, basically, we know this is a 10-volt battery. We have a resistor, we have a second resistor, and then we have our 4. This is our 4, 12, 6. And then this side gets reduced down to 1 resistor. That's going to be a 16 ohm resistor because we combined these two right there. Now, one other simplification that we can do is these two resistors are now in parallel. Parallel combinations are a little different than series, and they work like this. You have 1 over R equivalent is equal to 1 over 4 plus 1 over 16. Right? Now, the more, like if you can expand this to include as many parallel resistors as you need. So if I have like another one and then I have another one, it's just plus. Oh, okay, I thought that was a question. Plus, you just add them on to the end, right? But in this case, it's just these two. In this case, I would simplify this. I'd say, okay, this becomes 4 over 16 plus 1 over 16. And then this basically becomes 5 over 16 is equal to 1 over R equivalent. And then what happens there is we can just kind of flip this to R equivalent is equal to 16 over 5. And that should give us 3 point, what's 1/5? That's 3 point, is that 2? 3.2? Let me get my calculator. I'm just kind of eyeballing it. 16 divided by 5. Yo, 3.2. Okay, 3.2 ohms. So that basically means that this circuit goes positive, negative, resistor, resistor, resistor comes around here. So this is a 3.2 ohm. This is 12. This is 6. And then you just kind of keep going down. So now you're seeing that these 3 resistors are all in series. So you could combine all of these. So you'd say this is 18. 6 plus 12 is 18 plus 3.2. I'm going to say 21.2 would be the equivalent resistance. Let's look at the final answer. It'll load. Okay. Yep, 21.2. See, and this is exactly how they did it there. Does that make sense? iPhone? I hope it does.
Yeah.
All right. Perfect.
And so to get the voltage between, it looks like A and E, you multiply the 10 and the 21.2,
To
or
get the
what?
voltage between A and
Because that's what
E.
you're solving for, right?
No. So
Next.
in this case, we're just solving for this. So this is our equivalent resistance. Our voltage across this resistor is going to be 10 volts, just because it's one resistor, and then you have the thing there. One thing this does help with is that it helps you find, if you were to work backwards from this, you would be able to find, for example, the current flowing through each of the resistors, the voltage drop across each resistor. So for example, right, you have a 10-volt battery here, and then you have the 21.2 ohm resistor. Using Ohm's law, V equals IR, you know that current is equal to the voltage over the resistance. which would be 10 divided by 21.2, which is, where's my calculator? 10 divided by 21.2.
Yeah, I get what you're saying.
Yeah, so your amperage is 47.47 amps, right? So that's your I. We could actually do some questions later down the line that actually address just that too, which is pretty cool. I figured out why my webcam isn't working. It's because the camera's dead. So we're gonna plug that in for now. Hope that it charges, man. Oh, wait a minute. This ain't even plugged in. God dang. Julio. Okay. Did anyone else here miss our circuit reduction practice yesterday that has any other questions that would be relating to it? Because we can do
Questions like circuit D, when we have other components between the branches, does the rules of series and resistor, series and parallel still apply, or does that change a bit?
It can change a little bit. So, for example, circuit D is actually a really fun one because we actually had quite a discussion on that one yesterday. So let's draw out this circuit here. One thing that, let's see, let me just draw it out first before I say anything. I actually did it a second time today, and the way we did it yesterday was a little complicated for no reason. I put some comments in the recording though, that I posted on the YouTube channel, that kind of explains.
Ooh, definitely send the link to.
Yeah, I think I posted it in the notes chat and everything. It's the recording from yesterday. So yeah, so here, I'll gladly do this question again because it's actually a very good question. So one of the things first is that this question is formatted weird. This VX right here, when you look at it here, you don't really know what it's attributed to. If you look at the answer and the way it solves it, the VX is attributed to this resistor right here, the 3 kilo ohm resistor. So how does that help us? First things first, let's go through this question and let's label all of the nodes here. So we have node A, and then we have B. Oh my God, this is B. There we go. B out here. And then we have one more actually in here, and this is going to be here. That's going to be node C.
Okay.
So one of the things is that when you're simplifying this circuit, this is how you want to think of it, right? You're going to find the current through a branch, because that current's going to kind of, well, let's work through the whole thing and then I'll kind of explain my thought process. So one thing is, how can we simplify this circuit from how it is already? One of the things that may not be totally obvious is that these two resistors are in parallel, actually.
Yeah, that's true.
So if we look, I'm gonna combine both of these. So I'm gonna have 1 over R.
Wait, actually, hold on. Wouldn't they be in parallel?
Yeah, that's what I said. They're in parallel.
Oh, I thought you said series. My bad.
Oh, if I did, oh geez, now I don't know. Well, if I said they're in series, I meant in parallel. But
so would it just be 2.4 for those?
I think 2.4.
Oh, wait, which one are you asking about?
Are you asking about these two resistors in parallel here?
Yeah, they're in parallel.
Yeah, 4 and 6.
Yeah.
No. The
No,
3
3
kilo
and
ohm.
6.
This one.
Oh, no.
Oh no, the 4 would not be in parallel. Because for them to be in parallel, they need to share the same starter and the same finishing nodes. So if you look at this one, you have A and B here across this one. And then if you look at the 6 kilo ohm resistor, you have A and B as well, right?
Oh, gotcha.
So the way I usually
so as long as they share the same node, then you can say they're in parallel.
Yeah, like
same
in physics 2, they would draw them like this. So if this was 2 and this was 3 or whatever, you can see that they all start from the same, like this goes off to whatever up here, but this also goes off down to whatever. But this is like how it was presented to me when I was in physics 2. This is resistors in parallel. right? So they share the same in and they share the same out, right? It's like they're parallel to each other, the resistors. So with this one, I'm going to get 2/6 plus 1/6, 1 over R equivalent. So this is going to be 3/6. And then let's flip it. This is just going to end up being 2 is equal to R equivalent. This is going to be in kilo ohms. Does that make sense? That's a parallel combination. So if I redraw this circuit, I'm going to redraw it with the 2 kilo ohm resistor kind of on the outside. So this is going to go, you have your 12-volt battery here. Then I'm going to go, this is going to be my 4 kilo ohm. And this is going to go plus minus like this. And then we're going to have this is going to be our 2 kilo ohm right there. This is going to be our 4 kilo ohm. And then this is 0.5 VX.
So in this case, we lost our VX, right? Or is it still there?
So that's where this is actually a little bit, there's a little bit of an asterisk here because technically you did, but one of the things is resistors in parallel have the same voltage across them, right?
Oh.
So although Ms. Fahim would be inclined to tell you that, yes, you did technically lose it, this still has a VX charge here.
So does that mean that I know this is not the way to call it, but I still haven't memorized these names. The diamond shape component, that be 12.5 VX?
Yeah, that's a spoiler, but yes. But don't depend on it to be this simple because one little change to the circuit could actually throw not every circuit's going to work out this easily, right? Which is why we're going to, but yes, you would be right. So, because what'll happen is, okay, let's look at what our VX value is. We want to solve for this VX, right? So let's just do a KVL on the outside, right? So I'm going to go around this kind of around the outside. So we're going to KVL. This will be, let's say A, this is C, this is B down here. So we're going to go A to B to A. So we have a 12-volt rise minus, and then I'm going to say, let's see. Before we just do VX, actually, you could just straight up do VX on this one. Yeah, let's try it that way. Minus VX is equal to 0. Wow, the way we did it was so much more complicated yesterday. Oh, man. So yeah, VX ends up being 12. If you're unsure about this further down the line, one of the things that we're gonna need is we're also gonna want to find the amperage for the here. Let me get my notebook. I have a little bit of some notes written for this. Hold on.
Oh, I see what you're doing. So in this,
Hey, how did he get?
Miguel,
So did you multiply 0.5 times the 2 kilo ohm resistor
No.
to get the voltage
No,
VX
no,
is equal to 1?
No, that I did not do there. The
Yeah, wait, what? Okay, wait, your KVL's.
my KVL is weird. Hold on, it's not.
Yeah, it's weird. What you got that dependent source? You gotta factor in that.
Yeah, exactly. That's what was throwing me off here. So
And
okay.
then what else?
Yes.
Oh, that
So-
resist that 4K kilo ohm resistor. That thing definitely has a voltage.
It does. So yeah, ignore this equation I actually just wrote. So this is going to be a new one. So it's going to go 12 minus, and we're going to say 2 kilo ohms times, and then I'm going to put it. Oh, hold on. There's 2 people waiting in the waiting room. Can I admit all? Come on. Okay, they're joining. Sorry, I jumped the gun on that one. So this will be 12 minus the 2 kilo ohm resistor, and then I'm going to put 2 currents inside of this. These are my assumed currents, right? So my assumed currents are going to go. Can I put this like on the side? Okay. Sorry, this like the little zoom diagram is like really annoying to deal with sometimes. Okay. So my assumed currents Lovely. We're going to go like this. These are my assumed currents, like this. So this is going to be I1, I2, and this one's just going to be I, right? Okay. So this is going to be 2 kilo ohms times I1 is equal to 0, right? So what will happen is I'm going to move the 12 over. So I'll have negative 2 kilo ohms. I1 is equal to negative 12. And then I'm going to divide both sides by negative 2 kilo ohms. So when you're doing this, keep in mind, negative 12, that's going to be negative 2 times 10 to the 3. Does that make sense there? Because it's 2 kilo ohms. So with this, you're going to get what's basically 6 milliamps, or 6 times 10 to the negative 3. That's a 3. Right? What we're trying to find here is the equivalent resistance. So this is only gonna, this is like a small part of the whole picture. So what else do we have to do? This is when we start finding what Vx is in this case. So the way that I had done this was, okay, let's look back at this resistor that I have here. So this resistor here, let's not forget Ohm's law. So V equals IR. So my Vx across that resistor is equal to the current, which is 6 times 10 to the negative 3, times the resistance, 2 times 10 to the 3. Right? So when you plug this value in, you should get 12 volts. Right? This is the safe way of doing it, because like Eric was saying, our original KVL was a little funky in that it depends on the circuit, but this is a good way of checking our answer here. So the Vx is 12 volts. So I'm going to redraw this simplified circuit.
What was that? Wait, what was the problem asking for us again?
The equivalent resistance.
Oh,
Yeah. So now let's kind of scoot on here to the side. Let's just, for the sake of remembering, let's do KCL at A. So we know that I is equal to I1 plus I2. All right, because you have 1 going in, and this is going to be equivalent to the I1 and 2 going out. All right. Now we want to find what I2 is, because the thing is, we need to know all the information about the whole circuit so we can get the total current and like the total, kind of like the total resistance in a way, or no, I'm sorry, not total current, but total voltage in a way, right? Let's think of it. We're trying to find the equivalent resistance, right? So think of it like this, right? Our next, oh geez, sorry about that. Our next thing is going to be, we're going to be doing a second KVL.
yeah.
And what I did was I did a KVL that went kind of like, well, here, let me do, so this right here, this is going to be positive to negative right here. And my KVL went like this. It went in here, kind of like this. That was my KVL, right? So that KVL direction, let's write out the formula for it. One of the problems with this is that it gets really nasty really quickly. You get a lot of equations here. So this is going to be A to B to C to A. So we have minus, this is going to be 2 kilo ohms times the, this is going to be times the 6 milliamps here. Right? That's this right here. And then you're going to do,
by the way,
well,
for starters,
actually, wait,
we
we can
can
just say
a
that's,
dependent source. We already know what's gonna be because we know what Vx is.
yeah, so actually we could say that resistor is minus 12 volts plus, And then we know 12 times 0.5, that's going to be 6. So plus 6 volts here. This 0.5 times Vx becomes 6. Why isn't it erasing? Why does it do that? God damn. Six volts right there. And then this is going to be plus 4 kilo ohms times I2. And then this is all going to be set equal to 0. Now we just got to solve for I2. Right? So what we get from this is it looks like we're going to have, what is this? Negative
Yeah,
6.
0.0015. I hope that's right.
It 0.001. That sounds about right. Because look,
Yeah.
this is going to go
But,
negative 6 plus 4 k ohms I2 equals 0. 4 k ohms I2 equals 6. And you get I2 equals to 6 divided by 4 times 10 to the 3. And then this is going to give you, this is going to end up being 1.5 milliamps.
All right, yeah.
And that's your I2, right? So now, you might be looking at this and you're saying, okay, well, we have our current flow, you have current I2, we have I1, we have Vx. What do we do after this? Well, think of it. 1.5 plus 6 milliamps, that's our KCL here. So we know that I is going to be equal to 7.5. And then we know that our voltage, our Vx value is going to be 12 volts across this, this entire circuit, right? So V equals 12 volts. Well, you can even say Vx. Let's remember Ohm's law. So let's look at Ohm's law up here, right? We want to find the total resistance. So I could easily say our total is equal to the voltage over the current, which is going to be 12 divided by 7.5 milliamps. If I were to kind of write this out entirely, it would be 7.5 times 10 to the negative 3. And that should give you an answer of about 1.6 kilo ohms is your total resistance.
I got the answer too. I'm like, shit, this is big.
Yeah. So this is kind of this is actually a really good example of something we could expect to see on the quiz, right?
Yeah.
Question. We were able to deduce that the I is like the equivalent current because it splits into two.
Yes.
Yeah.
Okay.
What
about for like just the total voltage being 12? Like how
they gave that to us.
No, I know they gave, like, how do you know that that's like just like the max total?
Hey, what problem is this?
Because that's what they gave us.
This is
independent voltage.
This is homework 3, question 1.
Watch it. Yeah,
we know it's 12 volts. This is so my assumption as for why this works is that because the way I usually think of it is that resistors in parallel have the same voltage across them. And I know that this isn't explicitly two resistors in parallel, but I do see this as like, if I were to combine this as two elements, like if I had plus minus, I had my first rectangle, my second rectangle like this, that just makes sense for me. I don't know how solidly that holds up, but I've read the textbook for this class and nothing really explains it. Like there's nothing more that like gives more information.
The textbook is kind of cheeks, no cap.
Huh?
The textbook is kind of cheeks.
Yeah, it's pretty trash. It's pretty trash. Give me a quick second. Oh, Danielle's coming on in. All right. So how are we feeling on circuit reduction? Awesome.
Honestly, if you want to do another question, I wouldn't mind because I'm still a little iffy about it, especially since that's what's on our quiz.
Fair. Okay, let's see. So this is actually our
Appreciate
solutions. Of course.
Hello, okay. Miguel.
Welcome back. We're just doing a quick little review of circuit reduction, and I think we're gonna try to get in a little bit of what's it called? source transformation. I think that's a good one to practice. That one and what's the super node? That one's annoying to deal with.
Superposition. Did anyone email her and figure out if we have
Yeah, there
that?
was a dude that emailed her. He's waiting on her response, but she's probably not going to get back today. She tends to take her time on that sometimes. Yeah.
We can just ask her on Tuesday or whatever.
Yeah, exactly. All right. So this is a really good example for the sake of practicing. Okay, let's not write this so small. For the sake of practicing circuit reduction. So,
On Tuesday, is it circuit reduction or?
yes. Tuesday is only circuit reduction as far as I know. Okay, let's see. So here we have that. It's going to be 3 kilo ohms, 5 kilo ohms, 5 kilo ohms, 12 kilo ohms, 6 kilo ohms, and 4 kilo ohms. So we have current flowing through there, current flowing through here, current flowing through here. So this is going to use something called current division method. This is going to be IZ. Okay. So we have a total of 90 milliamps right now. So we know that this 90 milliamp current source, that's the amount of current that's going to be flowing through this whole circuit. So what I'm seeing here is, this is my thought process. We have 3 currents that this wants us to find. It wants us to find IX, IY, and IZ. Just looking at this, the easiest way would be to kind of combine all of this side, and this will all be in parallel with IX here, right? So this is kind of what I'm thinking, right? So here we have, let's do a few combinations here. This is going to be, oh, okay, look at this. So these 3 resistors are all in parallel. If you look here, let's label all of our nodes. A, B, C, C, and then this is all D right here. D, and this is all D, right? So these 3 resistors right here are all going to be in parallel. So to find the equivalent resistance, we do 1 over Req is going to equal to 1 over 12 plus 1 over 4 plus 1 over 6. That's going to end up, let's see, 1 over 12 plus 3 over 12 plus 2 over 12. So that's going to be 6 over 12. Oh, how lovely. So our equivalent resistance for this little spot is going to equal 2 kilo ohms. All right, you see that? So if we redraw the circuit, we're going to have, comes down, first resistor, that's our So this is going to be 3. This is our 5. And then we have our combined resistor right here. This is going to be 2 kilo ohms. And then this is going to be 5. Okay. If at any point you guys get lost on anything, just let me know. You know, because this is one of those things that it definitely builds, you know. Anyway. These resistors here are all in series. So let's combine those. The reason I'm combining them is because for current division method, we need just 2 resistors in parallel. So 5 plus, this is just going to be 10 kilo ohms.
We can have more. We can have more in parallel, technically. Well, I mean, yeah, I think for this case, it'll be easier.
Yeah. There are other ways of doing it if they're in parallel, but I haven't really. Okay, so let me see. Do I have a format written for it? I could have sworn that I had a format. Okay. So look at this, right? We have I of X flowing through here. Oh, actually, wait. Let me. Oh my God. We have I of X flowing through this side. That's what we want to find. And then we have, let's just say I of 1. That way I don't reuse any other terms. So to find I of x, this is the formula that we're going to use. Ix, this is going to be equal to the total current flowing through the circuit, 90 milliamps, and we're going to multiply that by the opposite resistor. So this is going to be 10 kilo ohms divided by the sum of both of them. So 10 plus 5 kilo ohms, basically. It's kind of like a ratio of sorts. So this is gonna go 90 milliamps, and then this is gonna go 10 over 15 kilo ohms, like this.
One quick question.
Go ahead.
Just to confirm, doing the was it current divider, I think it's called.
Mm-hmm.
We
Wait,
always
can you? Okay, go ahead.
you always take the okay, this is weird. This is like weird to like describe it, but like I'm saying is like what goes in the numerator is the resistor that is across from the current.
Yes.
Okay.
Yes. Yeah, it's really weird. But there's a bit of a not like a proof per se that you can do, but like you'll kind of see, like check it out. So this is gonna give us I of x. So let's punch this into a calculator. So the way you're gonna punch this into a calculator is gonna go like this: 90 times 10 to the negative 3 times 10 times 10 to the 3 divided by 15 times 10 to the 3. Right? And this should give you a value of 0.06 amps, which is just 60 milliamps. Right?
When you went from oh wait, never mind. I see it. Sorry.
Okay. So the kind of proof here is, look at it like this, right? We have two resistors here, right? And these are in parallel, and then you have your current source, whatever. This one's 5 on the left-hand side. This one's 10, right? If you're a photographer, think of resistance like the aperture on a camera. If you're not, then just think of it like this. The higher the resistance, the less stuff flows, like the less energy flows through it, right? So, because amperage stays the same, resistors drop voltage. But the point that I'm making here is that it's, oh, Xander's trying to join. Here we have 60 milliamps flowing through here, right? Through the 5 ohm resistor. The 10 ohm resistor is double the resistance of 5. So what's half of 60? Right? That's gonna be 30. Those two numbers add up to 90 milliamps. See how that works? So the 5 ohm resistor has less resistance, meaning more current kind of flows through that side, as opposed to the 10 ohm resistor. So hold on, give me a quick second. I need to get some water. Okay, give me a quick second. I'll be right back. Hold on. Okay, sorry about that. I'm back. Alrighty. Fuck, where did I leave off on? Okay, circuit reduction. Anyway, so we have 60 milliamps flowing through the 5 ohm resistor. So that gives us our answer for IX. So IX is equal to 60 milliamps. That's our first answer here. So now is when we start re-expanding everything, right? So we know that we have 30 milliamps flowing through I1 right here. So what we're going to be able to do is let's kind of take this back up and we can re-expand this circuit to, let's see, just about how much can we re-expand this to? We might want to re-expand this to, okay. Okay, let's see. Check it out. So we're going to have our current source here. This is going to be here. We have this, we have that, dot, and then we're going to have, now here's one thing. We want to keep this to just two resistors in parallel, right? So I'm going to keep this 12 ohm resistor here. Oh, Vic is trying to enter. All right. I'm going to keep this 12 kilo ohm resistor here. And instead of just splitting this up into the 3 different resistors like this, I'm just going to keep it down to 1 resistor. So instead, I'm going to have these 2 resistors combined in parallel. Does that make sense? My thought process here? Okay. As long as no one objects to what I'm saying, I'll just keep going. All right, so we have 1 over R equivalent here. So we're going to say 1 over 6 plus 1 over 4. That's just going to be, let's punch it into the calculator. 1 over 6 plus 1 over 4. This is going to be 12 over 5 for R equivalent. And that's just going to be 2.4. So this is going to be a 2.4 kilo ohm resistor on the right side of this equation. Is that fair? If anyone got a different number, let me know. So if you see the question here asks us, hey, what's IY? So what's the current flowing through this right here? Okay. Does someone have a question, or is it just okay? Never mind. So it's going to be the same thing. We know that through this branch here, we have 30 milliamps flowing, meaning that here's our formula. So we're going to find IY. IY is equal to the total amperage that's going to flow through, that's going to kind of split. So you have 30 milliamps, and we're going to multiply that by the opposite resistor. And then we're going to divide it by the sum of the resistors that are in parallel, meaning it's going to be 14.4 kilo ohms. If you guys want to punch that into your calculator, this should give you 0.005 amps, which is the equivalent to 5 milliamps. Right? So now we have our answer for IY. This is IY, 5 milliamps. Now we have one last one that we have to find. So let's redraw the circuit just one last time. Obviously, I don't have to draw all of the other, I don't have to label all the other components because right now they're not totally relevant. So again, think of it like this. We have 5 milliamps going through here. We have 30 going in there. So we have 5 going down here, which means that in this branch, we have 25 milliamps flowing. Right? That's just a basic KCL there. We know that this is a 6 kilo ohm resistor, and we know that this is a 4 kilo ohm resistor. And we have 25 milliamps flowing in, meaning that, IZ is going to equal 25 milliamps times the opposite resistor of 6 kilo ohms divided by the sum of both the resistors. And if you were to multiply all of that out, you should get 0.015 amps or 15 milliamps. This also works almost kind of like a ratio as well. So we know that IZ, which is the current flowing through here, if you did, let's see, hold on. If you did milliamps per kilo, so if you did 15 divided by 4, that's 3.75 milliamps per kilo ohm, which means if you multiplied that by, let's see. No, wait, I got the wrong numbers here. Oh, whatever. So we know we have 15 milliamps flowing through there. And by just kind of basic deduction, we could assume that we have 10 milliamps flowing through there. That's not a required answer, but it's good to know. It just makes sense. So let's look at what our answers are. So IZ, this one right here, I don't know why it's out of order here, but IZ here should equal 15 milliamps. IY is going to equal 5 milliamps, which we have right here. And then we have IX is going to equal 60 milliamps right there. And that's a pretty good example for circuit reduction there. I'm also realizing I forgot to share the notes from yesterday, so I'll do that after this call. But is this good so far? Is this making sense? Any questions? No? Awesome. Okay. Shall we try a source transformation, or what are dividers again? Hold on, let me look at this. Find the equivalent resistance, power dissipated.
Sorry, I had a current reduction question if you want to look at. That's like it has a weird topics. I don't know if you want to look at it. If I can share my screen and just show you.
Yeah, here, let's see. Let me stop sharing my screen here. And then let me change this to advanced sharing options. All participants can share screen. Okay, give it a shot.
Can you see my screen?
Yep.
So I had this problem. So it's a current reduction problem. So they want you to find like the equivalent resistance from A to B.
Okay. Yeah, so this is you mean circuit reduction is what this question is. Okay. Let me hold on. I have an idea. Let me try something here. I should be able to, okay. Here's what I'm gonna do. I'm gonna screenshot this. Okay, perfect. I'll draw it out and we can do it.
Thank you.
Alrighty, yeah. Let's see. So I'm just gonna change the screen sharing now. Okay, perfect. Now we're gonna do share screen here, advance screen. Okay. Oh dear. We're just gonna go back up to the top here. We're gonna get a new row. So let's see. I'm seeing one little issue with the drawing though. You have a resistor here above the A node that doesn't have a value. What is that value for it?
Oh, it was 2. I'm sorry, I forgot.
Oh, this is 2 ohms right there.
Yeah.
Okay. This is 7 ohms. And then this is going to go across a resistor there. It goes to a new node. It's going to be 10 ohms. Then this is going to go. This is 40. I have a 20 ohm there. Wow, this one's a messy question. Okay. Oh dear. 20. This is going to be 60. I'm seeing this line here as a short circuit already, but we're gonna see about that later. Oops. 4, 5. Okay. So first things first, when I'm looking at something like this 7 ohm resistor isn't connected to anything. So it's just a branch. No current flows through that. Right? Oh shoot, I messed up on drawing this. Hold on. This is supposed to fuck. All right. Let's try moving this up a little bit like that. There we go. Oh, goodness gracious. Just gonna draw it like that.
What kind of circuit is that, bro?
It's so bad, bro. It's so bad. Okay. Okay, here's the and then this has a line going up like that. Okay. Okay, so if I had charges between A and B, like let's say I had a voltage source or whatever, right? I'm seeing this wire right here, this connection wire. I see this as a short circuit between the 4 and 5. So I see this being totally negated like that, right? Now I'm gonna redraw this a little bit cleaner here. So it's gonna actually hold on. We're gonna scroll sideways and we're gonna draw it next to it. So I'm seeing. Here's what I'm gonna do. I'm gonna draw. What the hell? Hold on. Okay. I'm gonna kind of clean this up a little bit. You have one more resistor. This is 40, and this is 60. Okay. Let's label our nodes here. A, B, B, C, C, and then, well, I guess this is going to be D, E for this case. So this 10 ohm and this 20 ohm resistor are both in series. So time to redraw. So this is going to be 30. This is going to be 2, 40, and then 60. Now, if we label our nodes again, A, and then B, 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 we see these two resistors here are both in parallel. So we're going to have 1 over R equivalent equals 1 over 60 plus 1 over 30. I'm sorry, the way I'm doing this is really messy, but I'm just kind of like, this was like a really hard circuit to draw. But I have 1 over 60 plus 2 over 60. So this is going to be 60 over 3 is equal to R equivalent, which I think that's going to be. That's one. I want to make sure I have the right. Yeah,
It's 20.
20 ohms. So now I see we have a 20 ohm. So we have a 2, a 20, a 40. So I'm seeing the equivalent resistance is just going to be 62 ohms there. That's what I'm getting for my answer. Is that what you got, or do you have an answer for it?
Yeah, that's what I have.
That's what you got? Okay, awesome. Perfect. Yeah, with circuits like this, it's usually best to just kind of expand it out a little bit, like how I did here. Just kind of having things more clearly laid out. For example, with the short circuit that we had here, that was it was a little hard to tell here, but I'm sure that if I drew it out where it was more like here's my A, this is my B. If it was more like because think of it, right? This had a resistor here and then a resistor there. You could have easily said that it was just like this, like resistor in like that. And then you just could have said, yeah, just kind of like that. And that just kind of cuts it out. Something like that. That's a nasty one, though. That's a nasty question. Anyway. Shall I do some homework 4 maybe? Source transformations? Awesome. Okay. Use a series of source transformations to find current I naught in the circuit shown. Verify your solution by using node voltage method to find I naught. So I believe she said that node voltage method would actually not be on the exam. However, we're going to need to know it at some point, so it would be pretty good practice. But I guess let's just, well, actually, hold on. Where are my manners? Let me ask this first before we start. Does anyone have any other questions that they want to review for, oh, Danielle's back? Did she leave at some point? Anyway, anyone have any other questions regarding circuit reduction that they want to ask in terms of something hypothetical, theoretical, or an exact question? Or are we all doing good? Going once, going twice. Perfect. Okay. Let's do some source transformations then. Yeah. This is something that I'm actually not the best at, but let's see if we can just kind of get this figured out here. So there's that. Two milliamps. 2.7 kilo ohms, 2.3 kilo ohms, 1 kilo ohm, 0.6 milliamps. Okay. I'll let you guys get that one drawn out. All righty. Okay. Let's minimize this a little bit. We want to find I naught flowing across there. Okay. So one of the things is that with something like this, you might be inclined to try to reduce the circuits, not the circuits, but the resistors like this. You might try to say, oh, like maybe these are in series or maybe these are in parallel. That is not the case with a question like this. Just because of the nature of the fact that these nodes are not just, it's not an independent branch, you know, so you have AAA, you have BBB, and as you can see, there's more than just two things connected to the A, and then this is all just going to be C, 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 C. All right. So you have that. I'm thinking that with source transformations, what we can do is we can just this one right here is just a gimme right here. So one of the cool ways to remember how you do this is just V equals IR. So to turn this into a voltage source, you multiply the 2 milliamps by the 2.7, I believe. So if you do, if I recall, you could do, so voltage, if you wanted to convert this into a voltage source, I'm just gonna say the voltage source is 2 times 10 to the negative 3 times 2.7 times 10 to the 3. And if we punch that into a calculator, 2 times 10 to the negative 3 times 2.7 times 10 to the 3, we get 5.4 volts. Now, the way I usually think of it is the arrow is pointing to where the positive side is. So we have positive, negative like this. And then we go, the resistor goes in series with it. So then here we have the 2.7 kilo ohms. And then this is going to be this is going to be 2.3. And then this is going to go, this is just going to go like this. Now we have this side over here. So this over here, this is 5.4 volts, and this is 0.6 milliamps. The way I'm thinking of this is, I wanna like, I know that I have to do source transformation for this. I don't know if it's possible to have it up here. Okay, let's just keep going by the book. Does anyone know, does it matter which side the resistor goes on? That's one that I'm not too sure of.
What do you mean?
So when I convert this current source into a voltage source, like with this one, I put the resistor up here on the same side as the positive here. See? Whereas this, I guess it actually wouldn't change all that much. Negative plus, because then I would put the resistor here. This would be 1 kilo ohm, and then this is going to be yes, is equal to 0.6 times 10 to the negative 3. And we're going to multiply that by, let's just simplify, it's going to be 1,000 ohms. And then if we punch that into a calculator, 0.6 times 10 to the negative 3 times 1,000, I'm getting 0.6 volts is what I'm getting. So this is a 0.6 volt. So my question is, this resistor is here. Does it changes the circuit if I instead put it up here like that, right?
I don't think it does change. You'll get the same answer.
That's true, because we're KVLing, right? I'm gonna leave it here just for the case of leaving it. So let's do this. So this is, I'm gonna assume it would be I naught through the whole, it's all one branch, so it makes sense that you would have like I naught. So this is 2.7, this is 2.3. Let's just combine that. Let's just say this is 5.4 volts, and this is going to be positive here. This is a 1. So this is going to be 5 kilo ohms like that. This is 0.6. So now let's KVL it, because we still have our current flowing through there like that. So I'm going to say this is negative, positive, and then negative, positive like that, right? That way everything is positive to negative and whatnot throughout the circuit. So now I'm going to KVL this along with the current flow. So I'm going to go like this, right? So I'm going to start on the left side, minus 5.4 minus 1 kilo ohm times I naught minus 0.6. And then this is going to say minus 5 kilo ohms times I naught. And all that is going to be equal to 0. Oh, geez. Oh my God, why does it keep doing that? Okay, equals 0. That's kind of what I'm getting. Okay. So all I really see here is one variable. So I'm going to say this is -6 minus 6 kilo ohms times I naught is equal to 0. -6 kilo ohms, I naught is equal to 6. So then I'm seeing I naught is equal to 6 divided by -6 times 10 to the 3. We're going to have to pull up the answers for this, man. This one is wacky. I get negative 0.001 or -1 milliamp. Right? Okay, let's look at our answers here. Are my signs right? Okay, moment of truth. Here we go. Oh, -1 milliamp. Okay, hey, look at that. Nice. Off to a great start, ladies and gentlemen. We love what we see. Okay, any questions on that one? This is the work for it. Okay, awesome. No questions on it. We'll keep going. Damn, how long have we been going at this? It's almost 9. All right, let's keep going. Use a series of source transformations to find the current I naught in the circuit shown. Verify your solution by using, oh, we don't know mesh current method actually. Let's skip that one. I'm just only asked 3 questions. Should we do number 3, maybe? Find the current in the 10 kilo ohm resistor. Wow. God dang. Okay. Okay, this is not too bad. I don't think. So here's my thought process. Let's zoom this in a little bit. That's way too big. Oh my God. Okay, Alden. Welcome to the call, Alden. I think I can finally use my webcam too. I don't know if I want it though. Whatever. Okay. Anyway, let's keep going. So the reason I'm thinking this one isn't too bad is because I'm looking at that current source, the 12 milliamp current source, and I am seeing that as a way for us to do a source transformation on this question. After all, this is the source transformation homework. So resistor, 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 current source, resistor, 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 resistor. Perfect. 12 milliamps. So we have 100 volts, 20 kilo ohms, 80 kilo ohms, 3, 1. I gave up on writing all the things. Okay. 60, 5 current flowing through there. That's I naught. And then this is 10 kilo ohms. Okay. So what I'm seeing, let's label our nodes. A, B, C, C, D, E, 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 F, F. F. Okay. So I'm seeing a source transformation right here. So V equals IR. So this is going to be this is going to be, if we did source transformation, it would be 12 milliamps times 60. Then that's kilo ohms. Actually, see, that's why notation is important. And so that's going to be 12 times 10 to the negative 3 times 60 times 10 to the 3. Let's punch that into the calculator. 12 times 10 to the negative 3 times 60 times 10 to the 3. 720. 720 volts. God damn. That's a lot of volts. I think they
Isn't it
say- Go ahead.
better to change the voltage source on the left to current because we're trying to find the current? Or we're trying
Oh.
to find I know, right?
Yeah. Yeah,
So-
you're right. You're right.
I think maybe, I don't know.
Well, okay, here's what I'm worried about with that though. If we have that, we would have to, that would be a current source pointing down this way. And then I just feel like that's a lot of branches to deal with, right? I don't know. Okay, hold on. Let me think of this. Because couldn't we just KVL the, well, no, because the KVL wouldn't account for all of the inputs. Okay, you know what? Let's go with what you're saying. Let's see what we've got. Now you've got me thinking here. So wait. So in this case, would it be like these two that we're combining, even though it's like kind of funky? So it would be, so if we have V equals IR, we have I is equal to V over R. So that would be 100 divided by the 20 kilo ohms, right? So that would be 100 divided by, and then 20 times 10 to the 3. That would be 5 milliamps. Okay, so that's going to be, go down 5 milliamps. And then this resistor goes in parallel with it like this. So that's 20 kilo ohms. This is 80. This is 3. This is 12 milliamps. 60, 5, 10. So one thing that I'm personally thinking of is okay, so let's see. That's 60.
Can't we parallel the 20 and the 80?
Yeah, that's what I was looking at too. Yeah. Start combining some things. I was wanting to combine these resistors down here as well because same current is flowing through this entire branch. So it doesn't really matter all too much, but then again, there's no point in reducing it either if it doesn't make a difference. But yeah, let's do that. 1 over R equivalent is equal to 1 over 20 plus 1 over 80. So that's going to be 4 over 80. That's going to be 80 over 5 is equal to R equivalent. So 80 divided by 5, that's going to be 16 ohms, kilo ohms. So then this is going to be 16 kilo ohms, 5 milliamps. The resistor, current source, 60. And this is gonna go.
We're missing the 1 kilo ohm resistance.
Oh, yeah, I am right here, right? Thank you for that. I would have forgotten it. 5, 10, trying to find that. This goes there. 12 milliamps. This is a nasty one. I don't like this. Okay, so there's nothing we can do with the 3. There's nothing we can do with the 16. There's nothing we can do with the 1. Part of me wants to just combine this into 15, but that's not going to change a lot. Here's what.
Wait, Miguel, I'm sorry. I don't know. Maybe I might be reaching, but if we combine the 5 and the 10, can we use this 12 milliamp to get like the total equivalent of the circuit in that last fourth box? Or am I reaching?
I see where your head's at, but that's reaching a little bit just because okay, so combining the 5 and the 10, although in a technical sense, you're losing the I naught, you're not really, because keep in mind, resistors in series only reduce voltage, they don't reduce current, right? But if we were to simplify this side, just the 12 milliamps, you're still going to have effects from the rest of the circuit affecting how much can flow through that, you know?
Because we're also taking into consideration the current that's going through the 3 kilo ohm.
Yeah, and even then you're going to have the 5, like this 5 milliamp source is still going to have its effect on the entire circuit, I think. So I think I want to wear these. Someone's wearing something. Anyway, let's see. I'm gonna leave this like this though, just so it's like formal. It's nice. Let's see. What do we got? Okay. Let's. Let me think this. Let me see. This is gonna go. Damn. You know what? I say screw it. Let's simplify it. Why not? Okay, so we're gonna do. Wait a minute. Well. Okay, hold on. I don't have to totally rewrite the thing. Let's just do this. That's a big ass resistor, 15 kilo ohm. I'm gonna still say that has the signal in it. In a by the book sense, you lost the signal, but I'm saying we still have it. Okay. Let's see. Now this side, this is what I was looking at earlier. We have a difference in values here now, meaning that we should be able to what if we moved this here and then what if we did V equals IR plus minus this is our 1, this is our 16. 5 milliamps times, so what's 5? 5 times 10 to the -3 times 16 times 10 to the 3. That's going to be 80 volts. And then this is just going to go like that. It looks like we're kind of wiggling this into what we want it to be. Right? Like, I feel like we're kind of like shaking it down into 12 milliamps. So 16 plus 1. That's going to be 17. We simplified it. So minus plus 17. And this is 3. Wait. 80 volts. 60, 15, 12 milliamps. So we can't combine these in parallel because then we really are going to lose that signal. So there's no way she'd give us a question like this, right? This is like really fucking complicated. All right, let's see.
Oh,
All right. Okay, hold on. I'm gonna look at how they did it. Give me a quick second. I want to make sure that I'm not like wasting our time here. Okay. Let's see, I'll pull it up here. So this is problem number 2. Wait, which question is this? 3? Okay, yeah. So we start with this. Oh, okay. Okay. 5 milliamps. Okay, they combine it in parallel. 16. Okay, they put the 16 with the 1. Okay, what do they do afterwards? What? $20 kiloohms. Okay. 7. Oh, they combined these right here. So my guess is going to be that it doesn't matter what side you put the resistor when you're doing source transformation. And I think this shows that, because what they did, I think, is that I think they skipped the step here because everything else is the same. They combined these two things. Can you guys see my little stylus as I'm like writing around, or is it just like glitching on the screen for you guys? Ah, geez. So this, right, can I highlight at least? No. So 16 combines with the 1 that makes it 17. And then I think there's an intermediate step where they probably converted this back into a current source, had the resistor like that in parallel with it, where you have the 3 here, and then they just converted it back. But instead, they're like, oh, we're just going to put the resistor down here. So it's 17 in series with the 3. And then they combined it to make it 20. Okay. So note, source transformation doesn't matter where, or no, not where, which side resistor goes on. How did they do the earlier? Oh, look at that. They put the 1 kilo ohm on the top. I mean, we still got the right answer, right? So like you guys are saying, it's, you know, it's still right. So, okay, what did they do after that? Then they converted back to a current source. So current source, you have the 20 kilo ohms in parallel with it. And then, okay, they combine the current sources, which is fair. Current sources, these are just two forces that are acting against each other. Might as well just simplify it down to one. Convert it to a voltage source, put the 15 kilo ohm resistor in series. And then, oh, and look at that. And then you have basically this, and that's it. And then you just, 20. Yeah, they basically did circuit reduction here. This is all just a circuit reduction step. So at the very end, you had the 15 plus the 5 plus the 10, which this basically just says, hey, it's 30 kilo ohms, 120 volts. So you have I naught is equal to the voltage over the resistance, which is going to be 120 divided by 30 times 10 to the 3 right there, which makes that gives you 4 milliamps. Not bad. That's a nasty one. I don't like that. I do not like that at all. Okay. Shall we do, well, do they have any more source transformation questions? Right, this is the answers. Use a source transformation to bind V naught, find the power developed by the 520 volt. This is probably meant to say delivered. Power developed. Total power equals to the total power dissipated. So we're trying to find V naught. God dang. Okay. That's a rough one. How about this? Let's do a little bit of everything. Let's just go on to homework 5 here. Find the equivalent resistance. Find the equivalent resistance. Wow. Oh, this is that one guy asked. Well, actually, no, it's a little bit different, but for the circuit shown, calculate V naught, calculate the power dissipated by the 6 ohm resistor. Okay. These are all specify the resistors in the circuit shown below to meet the circuit criteria. This one was from the discussion. Okay, this has a lot of variety. I'm thinking something like this we might want to touch on tomorrow on the in-person, if anything, because it's starting to get a little late and I'm trying to go to bed a little early now. Does anyone have any specific questions they would want to go over before we call it or anything? I think this was a pretty solid study session. We knocked out.
Yeah, bro. I appreciate your help.
Oh, no problem, man. I mean, this is something you gotta be on top of this. Believe me, this stuff.
Can you post this? What you just did?
Yeah. I'll put this is the work from yesterday and today. So
I
I'll
wasn't
just
here
post the whole thing. Yeah, I'll post both of them. The video for yesterday is already posted. I think I posted it in